Hello there, ATS EVS 533 students. Dr. Shragi here, and I am giving you the promised lecture that is a review for the final in our class this semester. And the first thing I want to talk about is the fact that in our first module, which is all about observations of global warming and climate change, as I went through that, that's all material that people did really, really well on the first test. And it was all a really long time ago. And so, you know what, let's just not worry about the first module of the course because I think you guys have that mastered pretty well. I don't need to worry about that. So let's switch instead to wondering what we should know about the stuff from the second module. Now, the second module of the course was about the physics of climate, and we were basically framing our whole discussion in terms of how changes in temperature are related to changes in the internal energy of a system, in this case, the surface of the Earth. And these changes in internal energy then would be about the ratio of energy in to energy out. Now, energy in, of course, in the case of the Earth is, for the whole Earth atmosphere system, energy in is sunlight that it gets absorbed. For the surface of the Earth, energy in is both shortwave radiation that makes it through this atmosphere and longwave radiation coming down from the atmosphere. And that kind of gives us our first sense. I mean, we spent a lot of time on this particular diagram. Once again, I don't expect you to know the numbers or anything like that. That's not particularly important. But this diagram, which is based on observations, not models, not theory or whatever, makes a nice little conceptual model of how the Earth's energy balance works. And I think you should be able to label the arrows and so on to show how you understand how the Earth's energy budget works as to what all these different terms are. Um, it's going to be hard to answer the questions that I'm thinking about right without knowing terms like watts and joules, how watts are measures of power and joules are units of energy, and so on. I just thought I'd steer you toward that piece of information here. And you can see how, if based on observations, there is a very slight energy imbalance for the surface of the Earth, somewhere in the range of zero 0.6 to zero 0.9 watts per square meter. But there's high certainty that we are, in fact, having a positive energy budget. The surface of the Earth is having a net gain of energy. Then we started taking this apart into kind of a monochromatic way. Where is this energy? What is emitting this energy? What are we doing to the atmosphere that changes the energy budget, etc.? We made a series of these kinds of diagrams that showed the absorption as a function of wavelength, the monochromatic absorption, and the monochromatic emission of radiation by the surface of the Earth. And as we took these apart and put these together, we saw, for example, that there's a big range of the Earth's atmosphere that is big range of wavelengths, rather, that is by and large transparent to the wavelengths of radiation that the surface of the Earth is emitting. This was the so-called atmospheric window. These are wavelengths of radiation that there really isn't that much in the Earth's atmosphere that can absorb them. On the other hand, we had other ranges of wavelengths that the Earth is very good at emitting as well, and the Earth's atmosphere transmits virtually none of. And this is radiation that is already being absorbed by the Earth's atmosphere and also emitted by the Earth's atmosphere back toward the surface of the Earth before we talk about anthropogenic increases in greenhouse gases. So this is not particularly relevant either. We already absorb all of this radiation. It's these bands of radiation at certain ranges of wavelengths here where we have the atmosphere currently partially absorbs some of that radiation. The optical depth of the atmosphere there is neither infinite nor zero. We'll talk more about optical depth in a few minutes. But these gases in the Earth's atmosphere, things like, what do we have all listed in here? There's water vapor and nitrous and carbon dioxide and methane and so on. And what we see is that they are partially absorbing radiation at those wavelengths. And that means that as we increase the concentration of those gases in the atmosphere, we are increasing how efficient the atmosphere is at absorbing and then later emitting radiation at those wavelengths. Make sure you know a good dictionary definition of words like greenhouse gases and what they do and what bands of what types of radiation they interact with and so on. We used that so many different times this semester. I'm not terribly worried about that. I'm not going to have you actually put together a two-layer model. Again, this is the final. We're looking for bigger picture things like this, but I wanted to kind of point you to some things about the model here. Understanding what is doing the emitting, what is transmitting, or is this long wave radiation or short wave radiation, etc. What is what are each of these arrows indicating? Like if you were measuring radiation at the surface, which arrows are we talking about here? If you're measuring radiation from a passing satellite, which arrows are we talking about here? If we made changes to the emissivity, if we made changes to the transmissivity of the Earth's atmosphere for shortwave radiation, for longwave radiation, which numbers here would be changing? The actual business of setting up one of these is kind of beyond the scope of a final. I obviously would not expect you to actually be able to solve a system of equations like this, etc. And so, okay. So if we made some changes to this kind of model here, I just want to give you an example here on slide 22. If we originally had that the atmosphere was each layer of the atmosphere was absorbing 90% of the long wave radiation. If you change it to 50%, all the numbers in the energy budget change, and you get a slightly different set of 3 equations and 3 unknowns, and you end up with a new global mean temperature. In this case, it's much closer to reality. But the idea of like how would the temperature of the Earth change if the atmosphere transmitted more shortwave radiation? How would the temperature of the Earth's atmosphere change if the Earth transmitted more longwave radiation, and so on? Being able to think through signs and whether terms would increase or decrease, that's the kind of thing that seems most important to me there. And there's no doubt about it, we were able to make ways of trying to figure this out that were telling us important things about the transmissivity of these layers, but we were able to, rather than just make gross assumptions, let's assume the transmissivity of the atmosphere is 90% or 50%, we could use Beer's law to actually determine what the transmissivity of the Earth's atmosphere was. And Beer's law tells us that the monochromatic transmissivity of the atmosphere, that is, the ratio of the amount of radiation that's transmitted through a layer of the atmosphere to the amount of radiation that was incident upon the layer of the atmosphere, is this relatively simple exponential equation here. And I do want you to be able to understand how this term, we can, like on this slide here with the football field, we can rearrange it here. And I want you to understand what each of those terms are. What is I? What is En? What is B? What is delta S here? We use that football analogy there that might be helpful to you when you review. Beer's law tells us that this is going to be working for how radiation moves through some distance in the Earth's atmosphere, and together those 3 terms, NB and delta S, make up the so-called optical depth of the atmosphere. Remember, we decided to describe optical depth, which is a monochromatic property, as the extent to which the atmosphere resists the flow of this radiation at this wavelength. If the optical depth was 0, the atmosphere is not resisting any of that radiation. It all just transmits through. The layer is transparent. If the optical depth is infinite, then none of the radiation makes it through that layer. And if it's somewhere in between, then some fractional amount of the radiation makes it through. It's defined in such a way, it's kind of related to like how half-lives work when you're talking about radioactivity or something like that. It's defined so that an optical depth of 1 means that only 1 over E of the radiation that is incident upon the top of the layer makes it through the layer. Anyway, so I've got a slide here that just sort of steers you towards in day 3 of the physics lecture there, that how this is related to transmissivity and so on. But you can see here that we already have kind of some interesting ideas about the monochromatic transmissivity of the atmosphere and how it is related to monochromatic optical depth. At these ranges of wavelengths where we're not transmitting anything, the monochromatic optical depth is basically infinite. Oh, I'm sorry. Do I have this slide wrong? Hold on. At these wavelengths, the optical depth of the atmosphere is basically infinite. Yes, because we're not transmitting anything. Yes. Meanwhile, at these wavelengths, which are associated with the atmospheric window, the optical depth is quite small. I wrote on the slide basically 0. It's not quite that small, but the atmosphere is basically not resisting the flow of radiation at those wavelengths. And then there are these bands of radiation that we have a optical depth that's between 0 and infinity, and we are absorbing some fraction of the radiation now. But if we increase the number of absorbing bodies, N, by adding more of these greenhouse gases to the atmosphere, you can see how we're increasing the optical depth of the atmosphere, and therefore we are absorbing more of the radiation. We are resisting the flow of long-wave radiation emitted by the surface back into the atmosphere. So one way to think about the processes that maintain climate or change climate would be to think about ways in which we are changing the optical properties of these layers, and that is going to be resulting in changes in the temperature distribution. This led us on slide 35 here to a powerful term that we used for the rest of the semester, and that was radiative forcing. The IPCC definition of radiative forcing was that it was net change in the energy balance of the Earth due to some imposed perturbation, which might be a little bit hard to get in this context here, but once we saw it in terms of aerosols and greenhouse gases and so on, it became clear that that's sort of how out of balance the radiation, it's a measure of how much that factor, like changes in albedo or changes in greenhouse gas concentration, whatever, puts the Earth energy system out of balance. All right, now on that particular day, day 4 of the physics lecture, there's only the main thing I wanted to talk about on that day is about the role of water vapor, and I do want you to go back and review that. You might even want to go back and actually read those pages again, that like frequently asked text box on in the IPCC report about the role of water vapor in climate change. Water vapor is a powerful greenhouse gas. How come we're not worried about water vapor in the Earth's atmosphere in terms of climate change and so on? So anyway, that might be something that like could make a good essay question on the test or something. Day 5 of the Physics of Climate lecture is not something you need to worry about anything about. You can't have everything on the final. But day 6, we went into and talked a little bit more jargon here. We had words on that day like thermal inertia, which is about how it takes time for the temperature to increase. Again, physics people hate the term thermal inertia. They'd rather know about the factors like the specific heat and the conductivity and so on. But thermal inertia is a good way to kind of lump all that together. We know that the Earth is currently warming at a rate of, based on observations, of 0.6 to 0.9 watts per square meter. So there is some new temperature we're going to reach where we will then be in some new equilibrium, but we're not there yet. We have some committed warming between now and then where it's going to take, even if we walked away from the Earth right now and stopped having greenhouse gas emissions and so on, the planet would keep warming and not achieve that new equilibrium temperature for several more decades. Here's a more technical definition of radiative forcing that I like a little bit better than what the IPCC had here, where it's just defining radiative forcing as the difference between changes in the energy into the system and changes in the energy out of the system. Because we're changing the amount of energy in at the surface of the Earth, until we warm the planet up enough that we have increased the energy out, just by Stefan Boltzmann's law, we're going to keep having this radiative forcing. And we could talk about the radiative forcing of all these different factors in the climate system, stuff like trace gases, aerosols, land use, solar output, etc. In fact, we went through on one day of the lecture and spent like 15 minutes talking about all these different pollutants and their radiative forcings like carbon dioxide, methane, nitrous, halocarbons, tropospheric ozone, stratospheric ozone, and stratospheric water vapor. In the current draft of the test, by the way, this business of stratospheric ozone and tropospheric ozone has an ill-formed question in it. I like the idea about why is tropospheric ozone having a positive radiative forcing in the troposphere but a negative radiative forcing in the stratosphere. I like the idea about this, about how by depleting ozone in the stratosphere, we are no longer absorbing so much radiation in the form of ultraviolet radiation, but by adding tropospheric ozone in the form of a pollutant, we're increasing its role in the greenhouse effect. I like that. I'm having a hard time writing a good question about that, but you might want to review that basic idea. What I want to draw your attention to, though, is while carbon dioxide is certainly our biggest factor in this list in terms of radiative forcing, notice that actually if you add all the other ones up, they're about the same as carbon dioxide. In other words, we do need to worry about methane, nitrous, halocarbons, and so on, because together they are approximately the same amount of radiative forcing as carbon dioxide. We talked quite a bit about aerosols. Now, when we did aerosols back in that module, we spent, maybe 10, 15 slides talking about different types of aerosols. I don't mean like as in mineral dust and stuff. I mean like there were ones that were produced by the biosphere. There were ones that were secondary pollutants. I don't remember what they all were. But that list of like 5 different categories of aerosols is not important for the final. I would say worrying more about how those aerosols interact with terrestrial and solar radiation. And then some examples of these types of aerosols, like sulfate aerosols. Where do they come from? What is their role in terms of radiative forcing and so on? Again, we're mostly worried about sign here. Are these a positive radiative forcing or a negative radiative forcing? The black carbon is very dark. It tends to absorb shortwave radiation. It warms the planet. Mineral dust tends to be very reflective, and so it tends to have a negative radiative forcing associated with the ways in which we have an anthropogenic increase in mineral dust in the Earth's atmosphere, etc. Um, so these are the so-called direct radiative effects, where we're talking literally about like how the aerosol reflects and absorbs radiation. And overall, there's no doubt about it. Direct radiative effect for aerosols is about 0.5 watts per square. I'm sorry, negative 0.5 watts per square meter. They are in general cooling the planet. But there's also this indirect radiative effect associated with aerosols, where because they provide more cloud condensation nuclei into the clouds, and you get more smaller droplets. Instead of a few big droplets in a cloud, you get many, many smaller droplets, which has a much higher albedo. You get clouds that are more reflective. The classic example of this, of course, is ship tracks, where when a ship sails under a layer of marine stratocumulus clouds, the pollutants from like the diesel engines provide sulfate aerosols and things like that, and incompletely combusted hydrocarbons and so on that work for as lovely cloud condensation nuclei. And so the clouds are suddenly changed where they no longer have just a few relatively large droplets. They have vastly more smaller droplets, and the cloud then has a very different albedo. You can see how the albedo of the cloud has changed in these diagrams. Well, on a global scale, we've added a lot of aerosols to the Earth's atmosphere. Clouds in general are more reflective than they were in the pre-industrial era. Clouds can also change the cloud in an indirect way. They can change the precipitation rate and the height of the cloud and the ratios of ice versus supercooled liquid water and so on in a cloud. This is all part of the aerosol indirect radiative effect. Both the direct effect and the indirect effect are negative. They contribute to cooling of the planet with a relatively large negative 1.2 watts per square meter in terms of the radiative impact. On the other hand, these are relatively short-lived. Most of these aerosols are in the atmosphere on a residence time of on the order of like a year or two at most. Some are on the order of days. And so, we have this very big difference in timescale of the residence time of the greenhouse gases like carbon dioxide, which is on the order of centuries to millennia, and the radiative impact, the residence time of the aerosols, which is on the order of days to weeks to maybe a year or two, depending if they get up in the stratosphere, and depending on how hygroscopic, how easy they are to dissolve in water. Rain wash them out, and so on. And so there were other kind of radiative impacts that we talked about that day. We talked about how the changes of the surface of the Earth's albedo, changes in land use, changing areas from forests into crops, for example. That's a very common way to change large sections of the surface of the Earth. In general, crops have a higher albedo than old growth forest, for example, or rainforest. So you are changing the amount of radiation that's being absorbed. In general, crops have a different evaporation rate than the surface of the Earth. They all produce climate changes. There's also possible changes in the output of the sun. We talked about, for example, the sunspot cycles and the maxima and minima. The difference is actually between like the sunspot maximum and the sunspot minimum is actually a relatively large 1.0 watts per square meter. But keep in mind, that's the difference between the peak and the bottom of the sunspot cycle. Over the course of more than one sunspot cycle, it averages out to zero. So there's no net climate change from sunspot cycles and so on. But there are long-term trends in solar output that are both on the order of like billions of years as the sun goes through the normal stages of life of a main sequence star, and just relatively poorly understood like century-long changes associated with like grand solar maxima and things like that. But anyway, since the Industrial Revolution, we can add up all the radiative forcings, and we find out that we should have, since the Industrial Revolution, we would have had a radiative forcing of 1.6 watts per square meter, and we know that at the present time, our actual energy imbalance is right around 0.9 watts per square meter. So we know that we have already warmed the planet up enough that we have effectively canceled out 0.7 watts per square meter. Remember, we used the analogy of like a turkey in the oven. When you first put the turkey in the oven, into the hot oven, there's a very large imbalance between the amount of energy going into the turkey and the amount of energy going out of the turkey. But as the turkey cooks and gets warmer and warmer and warmer and is emitting more radiation by Stefan Boltzmann's law, then the imbalance gets smaller and smaller. And that's exactly what we're seeing on the surface of the Earth. We started off, if we had just imposed all these greenhouse gases and aerosols and stuff like that in 1750, we'd have had a radiation imbalance of 1.6 watts per square meter. In practice, sitting here in the year 2016, we have an energy balance of imbalance of about 0.9, which means we have warmed up enough already that we've canceled out about 0.7 watts per square meter, meaning we have a lot of committed warming still to go. All right, that was kind of everything I want you to understand about Module 2. Let's talk real quick about Module 3 as well. Module 3 was the modeling module, and the first day we talked quite a bit using those 100-level lectures as sort of our template as to what we were talking about. What was a numerical model? How was it different from like a conceptual model or a physical model? And how numerical models require that you have a computer program that understands the physical laws that are controlling whatever it is you're modeling. In our case, of course, the atmosphere. And as it happens, the physics of the atmosphere is controlled by 7 relatively easy to understand equations, at least to understand what the equation is doing. I mean, to actually write out the vorticity equation, which is one of the 7 primitive equations, the one that describes like how troughs and ridges form and so on, is huge. I mean, it takes like a whole piece of paper just to write the whole thing, and it's a complicated differential equation. We're not going to deal with that right now. But most of these equations have a relatively simple role. They're about changes in temperature, or changes in rotation in the atmosphere. They're about forces acting on air parcels. They're about conservation of water vapor, things like that. The 7 primitive equations. And we solve them at every grid point in a model. Now, the model grid points are a certain distance apart. That's the resolution. And they can be very, very close together, but you probably only want to do that if you have a regional model. If I was trying to make a climate simulation for the whole world, which is usually what you do in climate context, not necessarily what you do in numerical weather prediction, but in climate, you would want to have global, then you probably can't have the resolution all that great. The points have to be fairly far apart. We just don't have computer power to make a very high resolution global model. We set up these experiments. Now, we could do it in kind of a classic scientific method-y kind of thing where we're talking about like you have a control run, an experiment run of your model, and you make one thing different between the 2 runs, and then when you see how they change, then you can attribute the changes that you saw due to the one thing that you changed. That's a classic, kids learn that in grade school about how you conduct an experiment. We learned about the fact that the equations that are describing the atmosphere are in some ways initial condition problems and in some ways boundary condition problems. And boy, if you've taken differential equation or plan on taking differential equations, you know that this is radically different in terms of how you solve these kinds of problems and what makes a difference in these problems. Numerical weather prediction, the forecasting type application, is a very definite initial condition problem. And we talked, and I think on the test, everybody did really well understanding what it meant by an initial condition problem and how we get the so-called butterfly effect, where even very small mistakes or imperfections in our observations of the conditions at the beginning of a simulation end up growing into a terrible forecast. You would have a reasonably good prediction for a little while, but with time, the small errors grow to very big errors in an initial condition problem. That's in contrast to a boundary condition problem. Boundary condition problems are driven by external processes. And in the case of climate is largely a boundary condition problem. It is driven by things like solar output and greenhouse gas concentration and so on. A good way to keep these straight is that initial condition problems are when you're trying to predict the kind of things that are hard to measure at the beginning. Whereas so if you're trying to make a prediction of what the temperature is going to be 4 days from now, that's going to require incredibly precise observations and analyses of the temperature right now. In contrast, like a climate situation, yes, I still want to know the temperature at some point in the future, but it's what's driving it is things like greenhouse gas concentration and solar output. I'm not that those aren't the things I'm trying to predict. Those are the things I'm telling the model so that it can predict things like temperature. That's a good way to keep those straight. There was also, of course, this business about the differences between what we considered an answer in weather problems and an answer what we considered an answer in a climate problem. We're asking very different kinds of questions when we are studying weather and climate. And our main tool for doing this is going to, of course, be models. We talked about deterministic modeling, and we compared it to ensemble modeling. And those are good words to be able to know and to be able to walk through how we come up with what is an ensemble of models, how is each member of the model different than each other, and so on, and how we can use things like spaghetti charts to determine how long the models were in consensus and what consensus means and how that informs us about the range of possible outcomes. I mean, like, for example, on this slide here, we're just looking at the position of one particular contour on one particular plot, but you can see all the versions of the model at this point were still in agreement as to where that contour will be. All the members of the ensemble were in agreement or in consensus about what the forecast was at this point in the model run, whereas at this much later point in the model run, the models were out of consensus. The models are now no longer telling us really anything important about the weather at this, I don't remember what this was, someday in the future, 240 hours, that was 10-day forecast. So this is telling us, it gives us a sense of the uncertainty in or the range of possible outcomes. And we learned about this then as an ensemble of models. Now, in the case of numerical weather prediction, we make an ensemble of models based on slightly different versions of initial conditions. But for climate modeling, we can either make an ensemble that is based on a range of slightly different boundary conditions, or we can make an ensemble of models that are the same boundary conditions, but a range of different models. So we can use the same boundary conditions, but run the European model and the French model and the British model and the Japanese model, and we can see how there's a range of possible outcomes based on different boundary conditions and different model formulations and so on. No matter what, though, we're going to have to get a set of boundary conditions to apply in the case of climate modeling, and we're going to get these from these interdisciplinary understandings of the factors that are going to be influencing the carbon dioxide concentrations in the atmosphere in the future. Things like population and affluence and so on, but we'll talk about those in just a little bit. So apparently what we're going to be needing, according to day 2 of the modeling lecture, was we're going to need a set of boundary conditions to drive our numerical climate model. Well, that's going to be things like albedo and solar output and so on, but the one that's tricky for us is greenhouse gases. And we learn about how much we're going to be emitting globally by the IPAT relationship. And I think you guys were pretty comfortable with the population term and the affluence term. That T term is usually partitioned into carbon intensity and energy intensity because those are two different problems. The energy intensity is about how efficient we are, and the carbon intensity is about how much of our power we're getting from non-renewable sources like fossil fuels. Remember, based on these, the IPAT relation and interdisciplinary studies, a set of SRES storylines called A1, A2, B1, and B2 were formulated. Be sure you know the difference between the A's and the B's and the 1s and the 2s. That's a very straightforward thing to keep track of. And, they kind of simulated different paths about different storylines about what the future could hold in terms of the emissions and so on. And when these aren't just playing a game here. This is real understanding as to what is driving the climate and so on. And what we see here, based on realistic understanding of how fast we can adopt different technologies and how much they'll cost and so on, what we can see is, gosh, if this diagram here, which just shows us the carbon dioxide emissions, not concentration, emissions, gosh, even with really optimistic scenarios, we never really get all that low in our emissions. As we talked about on the third test, it's really only like the A1T and the B1 scenarios that ever get to 1990 levels of emissions, much less better than that. And all of them still involve big growths in the total amount of carbon dioxide in the atmosphere. None of them ever get back to pre-industrial levels. None of them ever get back to 1990 levels. on the order of thousands of years into the future. And we get these enormous radiative forcings, 4 to 8 watt per square meter. This would be on the order of some of the biggest things that have happened in climate in the last 500 million years. We can be seeing here that there are temperature changes associated with that large radiative forcing. There's a range of them that, depending on which scenario the real world plays out as being closest to, we have a range of warming of about 1.8 to 3.6 degrees Celsius by the year 2100. And of course, things get worse in the future. How high we let the carbon dioxide concentrations in the atmosphere get before we're off of fossil fuels. Now that's a very complicated issue in terms of our how we spend resources to look for fuels versus to look for alternative technologies and so on. But obviously, the higher we let the carbon dioxide concentrations get, the longer in the future we have this irreversible climate change. I mean, if we go all the way up to, say, 850 parts per million, where we're currently sitting at about 400 parts per million, 1,000 years from now, they still have 3 degrees of climate change. The climate has reached a new climate equilibrium that is way, way higher than pre-industrial climate. We describe this kind of global warming as being irreversible because it's very hard to get these carbon concentrations back down. Any individual carbon dioxide molecule is removed from the atmosphere on the order of a few hundred years at most. But the processes that remove it are generally respiration. Our photosynthesis, and that is generally not stored long term in wood and so on. It's the land biosphere quickly returns that to the atmosphere in the form of carbon dioxide due to respiration. And so it isn't that individual carbon dioxide molecules are going to be up there for thousands and thousands of years. It's that the carbon cycle as we have it now is mostly oriented around just spinning carbon dioxide through photosynthesis and respiration and just with no net change. The net transport of carbon dioxide out of the atmosphere is a relatively slow process. Okay. Day 3 was a fairly straightforward lecture that was just about the kind of changes that we can expect. Things like we have more climate change at northern latitudes than at polar latitudes than at tropical latitudes. Why? We'll have more climate change over land than over ocean. Why? We'll have there's more climate change in the northern hemisphere than over the southern hemisphere. Why? Make sure you can answer all those kinds of questions. On test 3, folks had a really difficult time with the question about Lisa Simpson and her blaming global warming resulting in more temperature extremes, including cold days and warm days. But in fact, that's exactly what the models don't say. The models are saying that the amount of cold days is actually going to diminish greatly on different RPC pathways. Just talking more about ways in which the climate could be changing, we see that it's hard to make good regional predictions as to what the precipitation is going to be doing, but overall there'll be more precipitation at the equator and there'll be more precipitation at the poles overall. And overall, know the things about the changes in the water cycle. More evaporation, more water vapor in the atmosphere, things like that. Okay, we spent quite a few slides of which this is a fairly typical one from day 3. Know that the sea surface temperature is going to continue to rise. Know the sea level height is going to continue to rise, etc. On day 4, I'm just putting one representative slide about that. Make sure you understand the difference between what's an SRES scenario and what is an RCP scenario. As in, what was the strategy? How was it different? People did well on this on the 3rd test, so I'm thinking that it wasn't necessary to just have a lot of review about this. Know a little bit about what would happen if the climate changed today. And I want to stop and show you guys something real quick here. On slide 99, there was this little spike in if we just stopped all our emissions today, there's this little spike in temperature for a couple years, and then the temperature starts kind of continuing to rise more slowly, and then over the course of thousands of years tapering off. Why the little spike was because of aerosols. Remember, the aerosols that we're adding are kind of hiding some of the global warming right now that are caused by greenhouse gases. If we get rid of the aerosols all of a sudden, then we're going to, they're going to quickly wash out due to precipitation, and we will no longer be hiding all that global warming. So that was what was that little detail. A couple people had trouble with that. Make sure you know about this concept of irreversibility associated with carbon dioxide in the Earth's atmosphere. Make sure you know about this concept of climate change commitment. Now, on day 5, we actually had I don't know, 4 or 5 different kinds of climate change commitment studies. That's not so important. But this idea about climate change commitment is important, and how we have to determine a target. What's the highest we're willing to let the temperature be, and how a consequence of that, a realization that if we have any limit whatsoever, I don't care what we set for our target as to how warm we're willing to let global climate get, then it's just a matter of when we get to zero carbon emissions, not if. We don't have a choice about stopping. It's just a matter of when. We do have a choice as to when we stop. A final thing to do from from that third module was to know about abrupt climate changes. The examples you guys gave on the test were reasonably good, but the definitions that folks gave for abrupt climate change were a little bit awkward. I would definitely say that I'm likely to at least have something as simple as like a true, false, or a multiple choice question to make sure you guys understood more about abrupt climate change. Here on slide 4, I have a mistake. It should say module 4, obviously, as we move on to the new material that's on the final. All right. Obviously, we had to cover this in a little bit more detail because it hasn't been tested before. And so let's talk about geoengineering. Make sure you know a good definition of geoengineering and how geoengineering efforts can basically be sorted into solar radiation management schemes or carbon cycle engineering schemes. Make sure you know a good definition of solar radiation management and how that means we're either going to reduce the amount of solar radiation that gets to the Earth by like building a shade or something, or we're going to change the albedo of the Earth so that we don't absorb so much of it. All right. We didn't spend just tons of energy at this point, on the sunshade possibility, because we had actually briefly talked about that earlier in the semester, and we had decided it was pretty impractical. But changing the Earth's albedo by injecting sulfur dioxide in the atmosphere or changing the reflectivity of clouds is actually well within the scale of what we could do and what we could afford to do. But there's a whole lot of problem associated with that. Namely, if we ever stopped doing it, then we wouldn't have any way, then those aerosols would quickly disappear, and all that global warming that we've been hiding by adding aerosols to the atmosphere would quickly be evident. We could also change the albedo of the surface of the Earth, usually talked about in terms of changing the reflectivity of built infrastructure, road surfaces, especially parking lots, the roofs of buildings, etc. By reflecting more radiation off of those surfaces, we would have the potential to change the global temperature. And I asked here at this point as to whether I thought those plans would work. And, well, the physics are good. I mean, we can certainly control the global mean temperature doing this. As we're going to see later, that doesn't necessarily mean we're getting back to a pre-industrial climate. There's lots of disadvantages to these plans, though. They're expensive. They have unintended consequences in terms of things like acid rain and so on. They're only focusing on the temperature, not other aspects of climate change. There's political problems associated with what if this results in unintended consequences for the climate in terms of like failure of the monsoons and so on. We have a lot of reasons why this is not maybe our first choice of a way to solve our problem. The second day of the geoengineering section, we talked about carbon cycle engineering, where we're trying to actually modify the carbon cycle so we get some of this carbon out of the Earth's atmosphere. And we could do that by, say, planting trees, which, are our best bet as far as sequestering carbon dioxide into the land biosphere. And we kind of showed that, there's a lot of uncertainty as to how much carbon that an acre of forest sequesters and how long it takes to grow and all this kind of stuff. But no matter what, we're off by orders of magnitude here. This is not enough to solve our problems associated with climate change, but it might be enough to prolong it buys us time. We can't solve our problems of climate change with the problem, but it does delay the time at which we would hit some target temperature. For example, one of the websites I pointed you guys to with a link that day showed that you could delay the date which you hit, say, a 2-degree climate change by on the order of a decade or more. And, well, that's a real thing. That's 10 more years we have for adopting mitigation strategies and technologies and so on. The reforestation efforts do also accelerate the rate at which we recover from climate change. So that's not to be dismissed. We also talked about the strategy of fertilizing the ocean to stimulate a biological carbon pump. The most commonly cited example of this is fertilizing the surface waters of the ocean with iron, because in many places the phytoplankton are limited. The limiting nutrient is iron. So you sail your ship to find an area where there's not enough iron for an active food web. You fertilize it, and you stimulate a phytoplankton bloom, and the food web goes nuts, and all the dead phytoplankton and the fish poop and everything ends up down on the bottom of the ocean, which is a way of sequestering carbon. Again, we talked in a later lecture about the fact that there's a lot of problems with this, and this is not at present allowed as a way of earning carbon offsets. It probably works, but there's environmental questions about this, and at the present time, this is not allowed as a carbon offset earning. I mean, nobody can stop you from going out and dumping iron, but you can't earn carbon offsets for doing it. Air capture, another possible technology. Literally just scrubbing carbon dioxide out of the Earth's atmosphere by chemical means, where the air flows over this very large surface area of these louvers, and the carbon dioxide binds to a chemical in there, and then there are chemical ways to use power to clean the solvent, and then you have carbon dioxide, which then you either sequester or use energy to produce a low carbon fuel or whatever. This is actually pretty slick stuff, and there are companies out there looking for startup funds and venture capital and so on to actually make this happen. At the present time, though, all of their economic models are a disaster. It takes enormous amounts of energy, so they have to spend enormous amounts of energy on renewable energy to pay to clean the carbon from the Earth's atmosphere, and then they don't really get very much money to either sell the carbon dioxide for use in like carbonated beverages or dry ice, or they have to, hope to earn carbon credits by sequestering it or something. This is just a business model disaster, and there's not a lot of point in trying to think about plans that have no real viable economic model. I mean, if we're just gonna be paying tax dollars to pay them to do this, there's better ways to do this, like burying biomass. Um, a big bamboo forest that you would cut down every few months and just bury the bamboo would be a much more cost-effective way to remove carbon from the atmosphere than air capture technology. All right. We talked about these other strategies like producing more peat or wetland restoration or burial of biomass or agricultural reforms as other ways in which we could improve the carbon cycle to get more carbon out of the Earth's atmosphere faster. And in general, these carbon cycle engineering plans look pretty good because at least they're dealing with the root problem, the carbon dioxide, not just dealing with the temperature. And so this helps with regard to ocean acidification and so on. There's a number of reasons why this is a good idea. And in general, the public likes these ideas because they don't require us to make changes in how we live our lives. As long as we continue to pay for some kind of geoengineering option arbitrarily far in the future, we get to keep doing whatever we want, like driving our SUVs. And from a policy point of view, that's easy to sell. It's also really easy to sell because these geoengineering options would produce effects very fast. If we started putting sulfate aerosols into the stratosphere, certainly within months to a few years, we would have observable differences in the global mean temperature. Whereas, like some kind of giant mitigation strategy, like a global effort to switch to renewable power, well, with the built-in committed warming that we're already committed to, it would take centuries before we would notice that this is any different than what we would have seen without the mitigation strategies. Yeah, we should be doing the mitigation strategies, but they're harder to sell to the public. There are lots of problems with geoengineering, like who gets to decide what the new ideal temperature is going to be, because there's going to be winners and losers no matter what you pick the temperature to be. What happens when geoengineering ends up harming one group but helping others? If your geoengineering effort causes the Indian monsoon to fail, you're talking about 1 billion people who depend on that for their water and their irrigation and so on. And of course, all the risks to other aspects of the environment, like, putting a bunch of sulfur in the atmosphere is another way of saying acid rain. So, none of these options are all that great. And that final day of the class, we said, are these actually going to work anyway? In the decades to come, probably we're going to think these are better ideas than we think they are now. Because in the decades to come, as climate catastrophes become more and more difficult to ignore, our descendants are going to think these are good ideas, okay? So we're going to need to know something about it. For example, what about that space shield, the sunshade kind of option? It would work in the sense of we could control the global mean temperature, but is it actually helping us achieve our goals? I mean, if we take a look back at an old equation we had for describing the amount of energy into the Earth atmosphere system, okay, we're controlling the value here of S, the amount of solar radiation that makes it through 93 million miles of cold dead space to the top of the Earth's atmosphere. We could control that temperature, that amount of radiation, which in turn would control the global mean temperature, and we would be fine. But the thing is, it controls all of the radiation by the same percent. If we're reducing the solar radiation by 2% everywhere, well, the problem is the poles already receive very little solar radiation. The poles, in fact, go 6 months of the year with no solar radiation at all. And so reducing that by 2% is 2% is zero. We haven't changed nothing at the pole. Even in the summer when they have long daylight, the actual flux of radiation is not all that large. So the total number of watts per square meter that's affecting at the poles is not very big. In contrast, at the equator, where the sun is high and the days are long, the flux of radiation is huge. 2% reduction in that is a large number of watts per square meter. Planet-wide, we have achieved the amount of reduction of solar radiation we want, but we have reduced the total amount of radiation up at the poles much less than we do at the tropics, but that's kind of the opposite of what we wanted. The poles are where the warming is happening, not the equator. We're changing the distribution of temperature in a very unnatural kind of way. We are probably making some small improvements like the ice albedo effect, but we haven't really done anything that affects the long-wave radiation, which is what is dominating the budget. In fact, we looked at a paper, Sunshade World paper from the AGU, and saw that this makes a mess of the climate. It costs trillions of dollars, and because of the differences in how we distribute and the difference in the time scales of solar radiation versus long-wave radiation, we never get back to anything that looks like a pre-industrial climate using something like a sunshade. And in fact, the same is true of any of our schemes. No matter what scheme we chose, if it was changing the albedo of clouds or putting aerosols up in the stratosphere, we can use those schemes to adjust the global mean temperature, but all of them do it in unnatural kind of ways that mostly result in the poles continuing to warm and the tropics continuing not warming as much or even cooling. And then we get changes in the global distribution of precipitation and stuff. We end up with a climate we don't like any better than the awful climate we're headed towards. And I showed you this slide just from a set of papers that shows that all of these have been examined, and the bigger the bar is here, the better the schemes did on that particular measure. And what I want to show you is none of them look good. None of them have big bars all the way across, right? They either have a problem in one aspect or another. None of them, either the problems are the costs are very high, or the rationale isn't very good, or the mitigation rate is too slow, or whatever, or they're not, whatever. They have a lot of side effects, or whatever. All of these then become bad plans. Now that makes us wonder, then what should we be doing? And we talked in a kind of a touchy-feely kind of way about what kind of things should individuals be doing to work on climate change mitigation. And the take-home message from a physical climatology point of view anyway is to spend your energy on the things that have a large carbon footprint. Commuting, laundry, airline travel, things like that. More so than small things. I mean, you go to the EPA website, it tells you every little thing matters. Yes, but some little things matter more than others, right? I mean, reducing your amount of time you spend in traffic because you combine trips and you commute less far and so on is a much bigger difference than remembering to unplug your phone charger, okay? All of these things, though, are just postponing. All these things individuals can do are just postponing the day when you have to reach a place where we're having emissions of zero. All these things have the potential to reduce the final temperature at which the climate equilibrates. All of these things are wise examples of stewardship. All of these things make the world better for our descendants. These are good choices to make, these individual choices, but there's no point in kidding ourselves. None of these things are going to save the world. We cannot recycle ourselves out of climate change. We cannot reforest ourselves out of climate change. None of these kinds of personal, individual efforts are going to get us out of the problem that we caused ourselves. They're going to be consequences for the choices that our society has made, and we can make things easier or we can make things harder, but all of them are going to be difficult. All of them are going to require long-term plans. All of them are going to require things that we're willing to spend money on, whether it's building solar power plants or wind power plants, or whether it's adaptation strategies like moving people out away from coasts when the sea level rises or whatever. All of these things are going to be expensive and are going to take long-term plans. But that's how we built the modern world anyway, is by spending trillions of dollars on infrastructure over long periods of time. We can do this. It sounds impossible when you just say, oh, we got to make we got to work, it's going to cost $500 billion to switch to wind power. We can do it. It doesn't have to all be one payment. We can do it over time, but we have to do it. And we need a plan, and we need a good plan. All right, that's the review session as far as I can tell. Please let me know if you have any questions. I'll get a review sheet to you. Probably by the time you see this, there actually will be a review sheet. And please let me know if you have any questions before the final.